Hi, the objective of this ICP is using the same data and the source codes that is provided in the class, but adding the two more layers to the encoder and decoder. Here we imported the libraries like Keras, TensorFlow libraries, and the layers, convolution 2D layer, dense layers, and the next batch normalization, and data sets like MNIST, losses like binary cross entropy, um, and NumPy and Matplot library. So yeah, I just loaded the MNIST load dataset to the input train, target train, input test, target test. So these are the shape of the input train and test, target train and test. So like 60,000 28 cost 28 size pixels, and 10,000 28 cost 28 pixels for test. So since the original is like so long and it takes lots of memory and requires more process time, so we are just changing from 60,000 to the 10,000 and 10,000 the 1,000 images for the train and the test. So these are the things. Next, showing the first 10 images in the train dataset. This is the 10 datasets, and the next these are the sizes of the reducer, uh, sizes of the input and target train and test. So we are configuring the model. So we got the size of the image width and image height is like 28 pixels, like the in data set we can see that MINST data set contains the samples that are 28 cross 28 pixels. So and the next batch size is taken as 128 and aperture is 50 apertures. it, each aperture contains a batch size of 128. So validate split is 0.2 and verbosity mode is set to 1, because which means that output shown should be shown on the screen, and latent dimension is equal to taking the two dimensional, and channel is equal to 1. So grayscale, we are using the grayscale data, so it's 1. Now we are reshaping the data, so that we use the input kind of shape and then reshape the data with the dimensions taken from the model. Here with input train, input test, and input shape, and uh, we just parsed the numbers as floats for the fast processing, speed up the training process, and then divided it. We are just normalized it by dividing the input train by 255, so that we'll get having the less value, so the which speed up the process. And then creating the encoder. So we have added two extra layers here to the encoder with filters 32 and 64 and node sites. And the function of this is like to get the fast process and less loss. So first thing, as usual, like first thing input, we're inputting the shape input, taking the shape and named it as encoder input, adding the convolution 2D layer with first 8 layers, and stride is equal to 2, padding is equal to same, and by the value activation function, and batch normalization, and next convolution 2D layer with 16 filters, 32 filters, and 42 filters, 64 filters. And then flattening to make it the one dimensional for the dense, and the normalization. And here we just finding the mu and sigma, latent dim, latent mu and latent sigma, and then getting the convolution shape of the encoder output. And then we are here reparameterization in the sense like in the neural networks, mean like we can see the gradient descent. So it will be using for or optimizing, and effect we can reduce the minimize the some effective losses that we are going to expected. So reparameterization helps us to reduce the losses. So we are doing using the sample as function, and then implemented the we just sampled and getting the z value from the computed mu and sigma values. So this is the function. We call the function using the lambda function, and then instantiating the encoder, the shape of the encoder, and next the decoder. So in decoder, taking the input, taking the input of the decoder, taking the output of the encoder like related two-dimensional, and name it as decoder input, and then just opposite of the encoder, like it's because it is a symmetrical. Autoencoder is a symmetrical shape. So doing the batch normalization, reshaping, and convolution 2D transpose. So we're just regaining the shape. So the filter 64, 32, 16, and 8, and then instantiating the decoder, and then we instantiate the variational autoencoder here, and shape of the encoder is like 28 cross 21, and output decoder output is like 28 cross 28 cross 1. And compiling and training. Compiling the autoencoder with optimized radom and loss is equal to binary cross entropy. We are configuring that here TensorFlow dot configuration dot run function eagerly of true, because if there is any errors coming out after the fit function, so it will take care of that one. It will overcome that one. And I have taken the 50 approaches. Next, the final is like visualizing the results. Visualizing the result after the encoder, like it is called visualization latent state function by defining, and then after the decoding, like a visualization decoded. So I just defined the visualization latent. I just call the functions by inputting the encoder data and decoder, like encoder, decoder, and data. This is the output. Thank you.